So thank you, everyone. I have the pleasure of being the last talk before the drinks, so I'll try to keep it on point. And the first thing I want to start a bit was giving a bit of an overview of where we are today. And we're all here to do something useful with quantum computing. And what we need for that is actually a lot more qubits, and they need to be a lot better quality. And this figure here shows the physical qubits, and then in colored areas where we can expect applications. And I've been collecting the last couple of years always what the recent advances are and where we actually are as a field. And you can see that we're clearly beyond the area we can classically simulate on our laptop, so to say. We're entering the NISQ era, but we're definitely not all the way on the top right in the promised land. And in fact, in order for us to get there, what we need to do is we need to really establish the quantum equivalent of Moore's law. We need to be, on an exponential scale, be improving the development of our qubits, of our quantum chips. But the question then becomes, okay, so how do we do that? And one model that I find particularly relevant, which we've borrowed from the semiconductor industry, is that of the yield ramp. And what's interesting is that every chip technology goes through this process in which you have an R&D phase, focused on figuring out what works in your architecture, a technology development phase where you're trying to improve the quality, and a manufacturing phase where you're selecting best chips. And the key thing is that because these have really different aims, they're also really different mindsets. So first we have the R&D, visualized here as a man really mapping out the landscape. It's an exploring, you need to be very versatile and adaptive, you need very smart, skilled people for it. Technology development is really about speed. You want to iterate as quickly as possible and get your fast feedback cycle to improve the chips. And finally, when you have reached the quality, you want to be selecting, cherry-picking your best hero device or hero chiplets if you're composing them, which seems to be a quite a good approach to go with. But what I want to talk about is this middle part. Speed is key. We need to iterate. But what does that mean? Well, quite simply put, we need to establish a feedback cycle between, on the one end, high-volume qubit producibility, and on the other side, high-volume quantum testability. And the last thing is what we as Orange Quantum Systems are specialized in. But you might be wondering why I'm putting so much emphasis on testing. And that's because what I'm telling you is we need to learn from semicon. But this is the key bit where quantum is really different than the semicon industry. So this is a case study based on some results Intel shared a couple of years ago. And I think this is not something that a lot of people here are aware of. But if you're looking at making qubits, we actually have the capabilities to produce these at an industrial scale. There's multiple qubit modalities that are compatible with industrial processes. There's many publications on this. But then once you have your qubits, and in this case, if we extrapolate based on the numbers Intel shared, they can produce 12,000 devices per day just from making wafers with qubits. But then to test them, you end up with 0.05 device per day. You're on a feedback cycle on the order of weeks. So it's quite evident that that's never going to work. And you might wonder, why is that? Is this an intrinsic property? And the answer is yes. And it has to do with that the fact to measure these quantum properties of the chips, you need to bring them to operating conditions at cryogenic temperatures with an elaborate qubit tune-up. And then we get to this thing that we're still in a very early stage of the industry. And how we used to do this, and luckily this is not always the case anymore everywhere, but this is how we used to do it. We had one system to rule them all, and if you ask the internet what a quantum computer looks like, they would tell you it's this. If you ask them about a quantum research lab, it's this. The chandelier is the symbol for all of these. But in reality, we have different systems with really different requirements. If you're doing research, you need flexibility, you need transparency, you need to know exactly what you're doing and adapt it as you go. You need highly skilled people for it. But if you're in industrial quantum chip testing, what you need is you need it to be turnkey and very, very fast. And if you're building a quantum computer, well, you need scale. You need it to be scalable to much larger systems. We're talking about these million qubit scales. And you want it to be stable for months on end and really push the performance. And until now, we've always sort of use the same way of thinking to build these systems. I want to focus a bit on this one because we recently launched our flagship system, the world's first industrial quantum chip testing system. And I want to talk about what it means. So the first property I want to talk about is turnkey. And this is one of these other ones that really sounds like an open door, but is really not standard yet in this maturing industry. So what does it mean? It's very simple. We need to define what this system should do and what that means. And in this case, it means that you have a user, you just put in like your design description, like what should the chip be doing, you put in your untested chip, you push the button, and a couple of days later, we're talking here 10 days, and that's already orders of magnitude better, you get out your test report and the qubits. So then the question is, how much better is that? Because the other thing, we're talking here about the quantum equivalent of Moore's law. And I wanted to share this figure. This is from our internal tech roadmap. We've actually realized this. But the most important feature of this figure is that the y-axis is a logarithmic scale. What we're trying to do is drive down this test cost exponentially. We really want to kick it down every single year more and more. And that's something that we're doing with innovations both in qubit automation, but also on the systems engineering, smart choices in our hardware, but also in talking to our suppliers. There's really everything there, because everything we make faster also directly, again, affects this cost aspect. Now, all of this has been realized. So we built this system. This is the OrangeQS Max. This is the world's first quantum chip testing system. And it's capable of testing 150 plus qubit quantum devices. So this is really up there with the largest quantum systems in the world. So I'm very impressed by that we were able to pull that off. But what I also want to highlight is a bit how we do this. What's the magic sauce here? And I highlighted here part of some of our engineers testing for the first time our user interface. This can also be operated completely remotely. And what we did is we actually built our very own quantum operating system, consisting of many modules, framework to program the experiments, the test protocols, the automation of the dependency between all these different protocols, libraries of this. We've been working many years also serving customers in the R&D market, but also the completely unique UI to control all of this, but also integrate the cryostat, automate thermal cycling, do some smart innovations to make these things work together. And last but not least, I'm very, very proud to announce that we've also sold this system to the European leader in quantum computing. Actually, literally today, I got the message that it's in a box on a truck to Finland. And in January, we're hoping to set it up. So with that, I'd like to give you a quick summary. Speed is key. And it doesn't come for free, because testing is a massive bottleneck in this industry that does not get the attention it deserves. And last but not least, a test system is not the same as a computer. So with that, I see I have 1 minute left for questions before you go for your drinks. So please, if there's any questions. And I guess if there are no questions, then I would like to thank you and wish you a very good night.